I'll say a couple of words about our plan. So this lecture, next lecture, we're talking about Euler and Hamiltonian graphs mostly, and then we have 3 lectures on topics that I posted in Telegram, so we just can vote until the following lecture, and I will discuss some of the topics. So if you have any questions about these topics, I can just give a briefly description of them. Because in Telegram you can, if you make a poll, you can only post something. Options will not exceed like 100 symbols, so I cannot write fully description. Yeah, so if you have any questions now, maybe in the end of the lecture, I will just give a comment about some topics that I give there. Okay. So if you have no, and I suppose that from the next time we'll continue to do some tests. So there will be tests on all following lectures, and then there will be a final zachot. It will be held on 15th of December, and so there will be. So I'll give you maybe some questions about the last lecture and the previous one, and you can just do some exercises to fire up your mark. Okay, so this was just like formal description of the end of our course. So if I want to explain what the question was given to construct Euler graphs, this is the 2 questions that we can ask when we're talking about graphs is, can we have all edges, all vertices in one cycle or path? So can we meet all the edges or vertices in one cycle or path? So I don't know. There are. I know what we discussed in the previous semester, but there is like a little difference between definition. So, for example, there are some terms like cycle, circuit, path, and so do you know the difference between them? What you when you say cycle, what do you mean by that?
Beginning of the path, one side is the end of the.
Yeah, what is path?
Path is the distance between one and beginning.
So if you're talking about path, we're talking just the sequences of vertices and edges. So we have like sequence V1, E1, V2, E2, V3, etc. Vn, such that such that the edge EG is just edge that's connected vertex VG with vertex VG1. So this is edge, this is vertices. Yeah, but now, and so cycle is when V1 and Vn are the same. But do you have restriction on vertices and edges? Because sometimes in some books they put restrictions that edges should be distinct, and vertices should be distinct. So what do you give? Hello. What do you give in your definitions? So what do you mean by cycle? Do you mean by or by path? So do you mean that all edges or all vertices are different? Yeah, yeah, something like some different words like trail and walk here, but and chain. So there are plenty of different words, but we need to. So I want to ask you what was the definitions of these guys in the previous semester, so we can just. So I just try to find some standard. Standard definitions. Let me see.
As a walk with no repeated vertices.
Yeah, so in path, you assume that all edges are distinct and the walk can contain the same edges many times, yes? And what about vertices? So do you have specific word for the paths which have all vertices distinct? Because usually in cycle, they're assuming that all edges are distinct and all vertices are distinct. But sometimes it's called simple cycle, and sometimes it's called circuit. But do you remember what was the definition in first part of the course? Because
yeah, a path doesn't have repeated vertices, and a cycle is just a closed path.
yeah, but do you have specific words for the cycle with no repeating edges, where with no repeating vertices? So okay, so let me then. Well, like make any like glossary here.
And we defined a trail.
So this is walk, and path is walk with no repeating edges. Okay, and cycle is path which is closed. Which is closed? Yeah. And how do you call cycle where all vertices are distinct?
Sorry, a path, we defined it with no repeating vertices, not edges.
Okay.
And a walk with no repeating edge is a trail, we call it.
Okay, so trail is walk with no repeating edges. Okay.
And a closed trail is a circuit.
Okay, and circuit is closed trail. Okay. Circuit is just trail with v1 equal to vn. Okay. Okay, so while we're talking about meeting all edges, if you want to meet all edges, we can meet some vertices several times. So when we're talking about one cycle containing all the edges, then we need not talk about cycle, but with the circuit, always trail. So, oh, sorry. So the best example is I just want to look at a picture just to be sure. So it's called Euler Trail or Euler circuit because Euler was asked about the questions of the bridges in Königsberg. Let me draw a picture. So we have like so in Königsberg there were like 7 bridges. Here, 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 and here. And Euler asked if there are, so can we go through all of the bridges? Can we cross all the bridges, but not crossing one? So each bridge will be crossing exactly one time. So in terms of graph theory, we have graph with 4 vertices and many edges. So we have like here 2 edges, here 2 edges, here 1 edge, here 1 edge, here 1 edge. And we want to ask if there is a trail that contains all the edges of this graph. And so of course we should meet one, so we can meet one the same vertex several times. So we talk about trail, not about the path. Because we can, the edges, the vertex can be repeated, but edges can be not repeated. We need to meet each edge exactly once. And so this graph, which is so usually the graph is called Euler is if it is contain Euler's socket in it. circuit that containing all the edge. Okay, do you understand how to solve this question? Can we meet all 7 bridges of Königsberg?
I think no.
Yeah, why is it so?
Because we neither have Euler circuit nor Euler.
So this is not big graph, and so we can just try to write all possible trails and see that we are not likely to get one trail containing all the edges. But can we say this about arbitrary graphs? So the question is, so we have graph with some edges, and the question is, can we or no obtain some trail which contains all edges inside of it? For example, we can ask the same question about like the edges of the regular polyhedron. So, for example, can we just start in some if we want to walk through all the edges of the cube, can we start in one vertex and then just have a trail containing all the edges of the cube, or for example, octahedron? So of course, if we have the triagon, then we can so we can just so the triangle is not big enough, so we can just try to find all possible trails. But if it's just big enough, for example, icosahedron or the dodecahedron, then it's much bigger. So we want to have some criterion here. And the main idea is that so if we have a trail, so for example, we start here and we go here. So for each trail, if you can see, then in each vertex without first and last one, we will meet only even times. So if we, for example, start here and meet some vertices, then for each vertex which are not beginning or the end of our trail, we just walk in and then walk out again, and walk in and walk out. And so we calculate only even edges of each vertex that are in the middle of our trail. This means that so in each of these intermediate vertices, we occur there even times. So we calculate only even number of edges. This means that if we have a Euler trail, then except for first and last vertices, all other vertices must have even degree, because if we provide the trail containing all the edges, that means that all these vertices, except from first and last one, must be of even age, even degree. So all and here we have a problem, because we have this vertex of degree 5, degree 3, degree 3, degree 3, and so we have 4 vertices of odd degree, which means that we cannot have a trail containing all the edges, because this happens if only we have no more than 2 vertices of odd degree. And the same holds for example, for cube. All these vertices have degree 3, and we have 8 of them. And so we cannot pass through all the edges here, because if you start, so we need to start or to finish in every vertex of the cube, and then we have 8 of them, but we should have no more than 2. And the same holds for the octahedron. Yeah, so for the tetrahedron, because all the vertices have the degree 3, and here we have yeah, but here we have all vertices have degree 4. Yes. So we have a chance to provide a trail here. Let's do the just try to. So what will happen if we try to provide a trail here? So we start in some vertex, they're symmetrical, they'll have the degree 4, and then we just try to walk somewhere, and then we can continue our walk. And so on the next step, let's just try to walk in other vertices if we can continue our trail. And so, as we can see, we can provide the Euler circuit here. So I just try to do as long circuit as I can, and suddenly I can achieve the Euler circuit. So, for example, for octahedron, we can provide an Euler trail or Euler circuit. So just closed trails. And in this, actually, in this problem, we have the actual criterion of graph to be Euler, or to have Euler path. And the answer is that if we want the graph to be Euler, then we need all the we need it to be connected, and we need to have all vertices of even degree. So the main theorem here the following statements are equivalent. So first, graph G is Euler, so contains Euler circuit, contains Euler circuit. G is connected, and all vertices have even degree. And the third, that G is connected, and all edges can be covered by the several cycles, several disjoint cycles. So for the last statement, it means that, for example, we can have we just have one cycle, second cycle, and so our graph is just the union of several disjoint cycles. So, for example, this graph is, so the edges can be, so the set of edges is disjoint union of several cycles. So cycles would, yeah. So here we have the exactly criterion for the graph to be Euler, that all the vertices have even degree and it is connected. And for the trail, we have another theorem. So this will be, well, maybe I should enumerate them. So theorem 1 will be about circuit, and theorem 2 that graph G has Euler Trail if and only if G is connected and have exactly 0 or 2 vertices of odd degree. We can say that so the number of vertices for degree must be even, so we can say here that it will be not more than 2 vertices of odd degree. 0, 2 is the same. Okay. Let's prove the first theorem. So it's easy to prove from first condition to the second. So if we already have Euler circuit here, then what does it mean? It means that we have some circuit that contains all edges of the graph. But if we calculate the edges that are neighboring to the fixed vertex, then we can see that in this trail we enter and go out of this vertex the same. So if we go in, then we go out from the vertex. So we can calculate. So we meet this vertex even times. So we calculate even number of edges which are near to this vertex, which means that all vertices are of the even degree. So if you look of our trail, then if we look all the places when we meet the same vertex v2, then we calculate even number of edges in there. So maybe I need to put some remarks here. First of all, right now I assume that we can have, again, this is like different terminology for the different types of graph. So when we talk about polar graphs, we can assume that we have several edges between the same vertices. And so maybe there's another name for this graph. How do you call the graph when we have repeated edges and loops? No. So usually you have, so usually by graph we mean that something that we can have only one edge between two different vertices and we don't have any loops. But I don't know how do you call graphs with loops and repeating edges, multiple edges. Again, I can have just try to see how this named in vocabulary. Yeah. Multigraph, yes. Well, the multigraph is graph with the multiple edges, but if you have loops, in some books it's called pseudograph. Okay, it doesn't matter right now, but of course, so if you okay, so we just can say that we talk here about multigraph here. So the graph can contain repeated edges, no problem at all. Then we can see that some vertices will have, so some between some vertices we will have 2 or 3 edges. Okay, so we calculate if we look at the same vertex, then we can see that we have even number of edges here, which means that each vertex has even degree. And of course, it should be connected, because if you have all edges in one circuit, then we can take a path, so we can connect every 2 vertices of the graph, because we just can use this circuit to connect them. Okay, and to prove from second condition to the first, we should prove. So we prove from the from 2 to 3, and then from 3 to 1. Okay, so maybe I will start here and then continue. So maybe I'll have enough place here. Okay, so I want to prove that, first of all, I want to prove that if all vertices have even degree, then we can cover all graph by several disjoint cycles. So let's do the same algorithm that I provide when I talk about octahedron. I just check that I can make a cycle. So if all vertices in G have even degree, then there exists a cycle in G. So maybe all have even degree, and there are the number of edges is not zero. Number of edges is not equal to 0. So graph is not empty. Then there exists a cycle in G. Why is it so? We just start in arbitrary vertex of non-zero degree. So if we have vertex of non-zero degree, then we can start and go out through one of the edges, and then we can assume that we the next vertex is V2. V2 has even degree, which is more than 1. It means that we have at least one edge coming out of the V2, and then we just choose arbitrary edges coming out of V2, and so on. So we just continue our walking here, and on each step we just choose arbitrary edge to go out of the next vertex. And so in each step we can continue our walking because each vertex has even degree. So sometimes in some step we will get to the vertex where we will already be. So for example, we go like V5, V6, and then we go to the one of the previous vertices, for example V3, and so we can have a cycle V3, V4, V5, V6. Maybe I write here the algorithm. So we start in arbitrary vertex V1, choose arbitrary edge E1, then we have V1, E1, V2, choose arbitrary edge from V2, and so on. And so now on each step we can continue working because all edges are within degrees, and it means that they are greater than 1. And then sometimes we will have this picture that V1, E1, V2, V2, V3, etc., Vk, Ek plus 1, and Vg, where G is strictly less than K. And so we will meet one of our previous vertex and one of our previous vertices, and so we will have a cycle here. We obtain cycle. Okay. So if all vertices G has even degree, then we always can obtain cycle. But then we can just forget about all the edges of the cycle. So if we have cycle V1, E1, V2, E2, Vn cycle, then we can consider the new graph just cutting off, forgetting about all these edges. If we drew these edges out, we have cycle here. If you drew all the edges out, it means that all the degrees of all these vertices will be down by 2. So, but if but if degree of all these vertices are even, it means that if we subtract 2 from them, that will be remaining even. And so in U graph, we will have again all vertices will have even degree. Again, all vertices have even degree. So again, we start from our graph, find cycle, then forget about all the edges, and then we have new graph where all vertices have even degree. Again, we can find cycle there, and so on until we have no edges. And when we have no edges, it means that the edges will be just the disjoint union by several cycles. So we start from the connected graph and we finish with connected graph, and all the edges will be covered by several disjoint cycles. Okay, let's prove then 1 from 3. So now we have connected graph where all the edges covered in several disjoint cycles. And we want to have we want to provide a circuit here, another circuit that contains all the edges. So we just have several disjoint cycles, and then we just do the following procedure. We take cycles which have common vertices, and then we make one circuit from them. So we have several cycles. Let's do the following procedure. If so, procedure, two cycles with common vertex, we will have one circuit. It is so if we have two cycles, suppose they will have the same first vertex. So we just start and going through one circle, first circle, and then continue to the other circle. So we obtain the circuit like the following. Just the union of these two cycles. And we have one circuit. So if we have one circuit here and one circuit here, then we can just go through each vertex of one cycle, then go to the other cycle. So we will have one circuit containing all the edges of these two cycles. So in each step we have the less and less number of circuits. We now have the disjoint circuit that containing all the edges, and so the process will be stopped, and will stop if we have several circuits. It means that the non-intersecting, and this means the graph is not connected. So if so we continue, but instead of cycles we have circuits here. So we just take two cycles with a common vertex and make one circuit. Again, take two circuits with common vertex and make one circuit from them on the same procedure, and if procedure stop, so either we have one circuit, it's okay, it means that we have Euler circuit that contains all of the edges, or another possibility is that we have then it means that our graph is not connected, because procedure stop when we have all circuits with no common vertices. If we have circuits with no common vertices, it means that our graph is not connected, which is not true, because we suppose in theory that it is not connected. Contradiction. Okay, so we have our Euler circuit here. Of course, it's not. So there are different possible proofs, because we can just try to provide. So we can start from 2 and then can just get straightforward to the 1. Just so we can just try to start in one vertex and just construct the Euler circuit. So we go until we meet again in the vertex v1, because we can just go and we will not stop until we get in v1. But now there is a small problem, because we cannot go from v1 to anywhere maybe, but there maybe we have other edges that we need to cover. So we need to look at if we have some vertices we have additional edges, and then start from there, and then try to construct again some type of circuit, and then we will add more and more edges to this path. So for example, if I do, so when I was talking about the octahedron, so if I start from this vertex, then I can do the following. I can go through this vertex and then from this path, and then so I just walk through all the edges that neighbor into this vertex. So I have 1, 2 that adjacent to this vertex. So I have 1, 2, 3, all 4 of these edges. But some of edges are left in my graph. So to add them to the circuit, I need to add this to the other part. So I just need to, for example, start here and go through this cycle and continue here. So again, if we do this straightforward from the second statement, then we need to be accurate to count in all of the edges. Okay. Okay, so let's talk about the Euler Trail, and then we will have a little break, I suppose. Okay, so what about the second statement, second theorem? Maybe I should bring this. So we just proved about the conditions of graph to have an Euler circuit, and now Euler Trail is the trivial corollary, because so suppose, first of all, if G has an Euler Trail, okay, so I'm talking about the proof of the theorem. If J has an Euler Trail again, we can calculate the number of vertices with even degree. Except from the first one and the last one has even degree. This means that only these two guys can have the odd degree. So this means that we have 0 to vertices 0 or 2 vertices of odd degree. And this is from left to the right and from the right to the left. So we have a graph which is connected, and we have 0 to vertices of odd degree. So G is connected, and has 0 or 2 vertices of odd degree. Okay, so if you have 0 vertices of odd degree, that means that all vertices have even degree. And this we prove already that the graph G is Euler, so we have Euler circuit. G has Euler circuit. But if we have Euler circuit, of course, we can look at this as trail, but just so the circuit is just a closed trail, so of course it has the same will be trail. The same circuit will be trail, Euler trail. So we already got what we wanted. But if we have two vertices, then we just can connect them. So we just can add one edge that connected these two vertices. So suppose V and W has odd degree. Let's look at the new graph, which is obtained by the previous guy by adding the new edge connected V and W. So here I just use the notation of multigraph because maybe there was already edge between them, and now I add the same edge twice. But it's okay because I consider multigraph. And now G is Euler by the proof of the theorem. So now all the edges will have even degree. Then we have an Euler circuit here. And if it has Euler circuit, then we can just look at the circuit and just cut this new edge from the circuit, and we will have Euler Trail in the previous graph. So I will take a picture. So now we'll have in like some circuit, and somewhere here we will have new edge that we add. So suppose this is the edge between V and W. That means that if we cut this edge from this graph, then we'll have the remaining part of the circuit will be the trail that we need to construct. So if we have like if the circuit is So if this is an Euler circuit, that we can just take the part, this part from the V1, V2, V2, etc. V minus 1, E and W, and this will be the Euler trail that we need to find. So it's if we prove already the criterion for the Euler circuit, then we can get the Euler trail easily from that. So I want to discuss one of the application of Euler circuits. How can we use them? And the application is actually using in bioinformatics, know how to pronounce it, and it's called De Bruyn's sequences. What is these sequences? So we just fix the elements of the alphabet. For example, we have just 0 and 1. And we want to write a sequence which contains all keywords. So as the subwords, they contain all different keywords from this alphabet, and each word should be appearing only once. So we fix the number k, natural number, and we want to either maybe just definition. The Bruyn sequence sequence is sequence from of elements from A such that of elements from A such that it contains each of word of length k exactly once. So for example, we fix the alphabet with just 0 and 1, and we want to wrote a sequence which contains all words of length 2 exactly once. So this would be like 0, 0, 1, 1. So by contains, I mean that we have a subword. So we just can take the so I take only elements that go together. So in each subsequence of length 2, I will have all different words of length 2. So here will be 0, 0, 0, 1, and y1, and 1, 1. And for example, for length 3, so if I want for De Broglie sequence for 3, I will need to have a sequence which all subwords of length 3 will be covering all the sequences of length 3. You will just, so I'll try to wrote some sequences like maybe no, I should write something like 0, 0, 1, 0, 1, 1, 1, 3, 6. No, there is no. Mm, 0, 0. Yeah, should have 1, 0, 0. Yeah, something like this one. So I have as subsequences, I will have I will have 1, 1, 0, then 1, 0, 0, then 0, 0, 0, then 0, 0, 1, 0, 1, 0, 1, 0, 1, 0, 1, 1, and 1, 1, 1. So I have all different, so they will be different. As they will be all words of length 3 from this alphabet. So exactly 8 words. Okay, so from the definition, you will get so the length of De Broglie sequence if the alphabet contains n letters and we have length k. So what is the length of the sequence will be? So for alphabet of 2 symbols and words of length 2, it will be 4, and for the alphabet of 2 symbols and all words of length 3, it will be 10 elements here. And what's the formula for arbitrary n and k? Sorry, 2 and 4? If we have 4, no. 18, I suppose. So we need to have like how many words of length k do we have? The word of length k is n to the power k, and now if we have all them, then we need to just look at the so we need just so the first element of the sequence will be n to the power k, and so we just need to add the ending part, which is like k minus 1. Yeah. So for example, for n equal 2 and k equals 3, we will have exactly 10. 2 to the power 3 is 8 plus 3 minus 1. Okay, so the main the main question is there exists such sequence always, and is there any simple algorithms to find it? So is sequence always exist? for each A and K, and if yes, do we have an easy algorithm to find it? Because sometimes you have the existing theorem, but it's not easy to find such sequence. You need to try all the sequences of length of such length and try to find all the words there. Okay, but in our case, the questions for both answers is yes, so we can yes. We always this the sequences. There are many of them, and yes, we can provide a not so hard algorithm to find each of the sequences. And first, so to prove that we always have different sequence, I just first illustrated this by writing some graph connected to the sequence, and then we'll discuss what does it mean that we have a different sequence, and why. So how we connect it to the graph, and why we can prove the existence, and then we discuss the algorithm. So which it will be. I will give an example just for 0, 1, and x3. So first of all, I need a beautiful picture. I will write a graph, and exactly the different sequence will be the Euler circuit for this graph. What is this graph? This graph will contain all vertices of my graph will be all words of length 2. So there will be four vertices, 1, 1, 0, 0, 0, 1, and 1, 0. And then the edges is the connection between the words, which means so it's all words of length 3, and the beginning of edge will be the first two elements of the words, and the last two elements will be the ending of this edge. So edges will be words of length 3, and if I have ABC, then it is connection between AB and BC. So I will try to illustrate this in picture. So for example, if you have 1, 1 and 1, 0, this will be connected by the word 1, 1, 0. 0, 1 and 1, 0 is connected by the edge 0, 1, 0. Here is the edge 1, 0, 0. Here is the edge 0, 1, 1. Here is the edge 1, 0, 1. Okay, 6 will be this one, going 0, 0, 1, and I have two loops, which is going from 0, 0 to 0, and from 1, 1 to 1, 1. But in arbitrary situation, I will have so graph in for arbitrary a and k will contain, so the vertices will be words of length k minus 1, and edges will be words of length k, and we look at the this words of length k, and it will be connect vertex of the first k minus 1 elements to the last k minus 1 elements. So we have a picture, we have a graph. So this differs from the discussion about Euler graph because this graph is oriented. How do you call oriented graph? Or graph, directed graph? Directed, okay. So this is the directed graph, yes. So because is now we have each edge has end the beginning. So it goes from one node to another node. Okay, let me just focus. And what does it mean that we have the De Bruijn sequence? De Bruijn sequence means that we have an Euler path in this graph. So we need to have a path that goes through all the edges of our graph. Why is that? So for example, we construct, so let me draw some example. So for example, we need to provide some circuit. Let's go here, 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 and here. And then we will write this trail. So we'll make the trail from this. From the trail, we can make the sequence. So we start from the edge 1, 1, 1. Then we continue to the edge 1, 1, 0. So if we continue to the edge 1, 1, 0, it means that they have common. The end of the first edge is the beginning of the second edge. It means that the ending of the first word is the same as the beginning of the second word, which means that we can have we stand through the sequence. Again, if we end it in the vertex in the node 1, 0, it means that the first part of the next edge will begin from 1, 0. So we can just get the sequence from the Euler trail. So we'll have 0, 0, 0, then we have 0, 0, 1, then we'll have 0, 0, 1, then 1, 0, 1. And then we will have, okay, but I just missed it. Yes, I just wrote the wrong picture here because I need to go under the and the upper. Sorry. So I need to go here and then here. Yeah. So it will be 0, 0, 0, 0, 0, 1, 0, 1, 0, 1, 0, 1, and 0, 1, 1. And so I just wrote the example of the de Bruijn sequence. Actually, here we'll have the Euler circuit, not trail, but it doesn't matter. So okay, we can row them into the in circle way, not as a circular sequence, but it's not the point right now. So we have our de Bruijn sequence just as Euler trail in this graph. So if you want to prove that always have this is the Bruijn sequence, we need to prove the version of our theorems for the directed graphs, and then just check that this graph has similar properties, the same properties as it is in the theorem. Okay, so we need to prove theorem for the directed graph, and so a directed graph. So the definition is the same. Of course, if we have the directed graph by the trail, walk, path, cycle, circuit, we have the same definition, but of course we need that in this walk the edge. So if I wrote v1, e1, e2, v2, it means that v1 beginning in the v1 and end in e2. So this path has direction. So we have all the definitions we can say for the directed graphs. So the directed graph is Euler if we can provide a cycle, a circuit which contains all the edge of this graph, and of course it will be oriented circuit. Is Euler if and only if it is connected, and so in usual graph we just say that the degree of all edge of all nodes are even, but now we can say that for each vertex the in degree is equal to the out degree, and for each vertex in degree is equal to the out degree. We have specific names for this degree, so so in degree is the number of all edges that go into this vertex, and out degree is the number of all edges that go out of the vertex. Yeah. Yeah. So it's about Euler circuit and the Euler trail. As usual, we just say that. I can just mention it here. So as Euler trail if and only if it is connected and for each vertex except maybe two. The same holds, so in degree is equal to the out degree. And for these two nodes, they differ by one, and in one vertex we'll have in degree less than out degree, and in other vice versa. So another will be bigger. So and for these two, one in degree is out degree plus 1, and second is minus 1. So actually, it's a long theorem, but I think you understand the idea, because if you prove that for Euler circuit, of course the same idea will hold for the trail, because if you can, if you can make a new edge such that it will become Euler graph, then we can have the trail, and otherwise we can have trail. So if you have a trail, then of course we'll have, so all degrees will be, so all in degrees will be equal to out degrees, except for first and last element of this trail. And for the first element we have more out degrees, and for the last element we have more in degree by 1. So okay, so what about the proof? The proof is a similar the proof is similar to our theorem, our first theorem about the Euler graphs, but I'll just say a few words about it. So I will just go throughout the proof and just say a few comments. So of course, if direct graph is Euler, then of course it's connected, and of course if we have an Euler graph, then if we look at that circuit, then we can see that we enter and go out from each vertex at the same time. So if we look at this circuit, then we can see that if you look at the arbitrary node, then of course we'll have, so this will be counted in degrees and out degree, and so in degree is equal to out degree. And if you want to prove that if in graph we'll have all vertices will have in degree and out degree the same, then we just do the same idea. So we just start from arbitrary, we take the arbitrary node, then we go, so it is connected, then we have the some edges go out, then we meet other node, then since in all degree of this node are the same, then of course we can go out from this node, because if we have in degree 1 greater than 1, then out degree is also greater than 1, and so on. And so we can walk until we get a cycle, or maybe we can just go until we go meet the first vertex, and then if it is maximal possible circuit in this graph, with the circuit containing maximal number of edges, so if it contains all edges, then we're finished. And if it will contain some other edges, then since graph is connected, then we can have some vertex of additional edges going out, and so we can construct some circuits that contains more edges, and so we can contradiction, then we have the circuit that containing all edges of this graph. I just say the same words, but give you another proof of the existence of Euler circuit here. And for Euler Trail, as I said, the idea is the same. So the all difference that if you have a trail, then we can start in one node and end in another node, and so we can connect this node by the appropriate edge directed into from last vertex to the first vertex, and then we'll have an Euler circuit, and so we can use the previous criteria. So the idea is mostly the same. Okay, so returning to our problem, now we just, so if I want to prove that there exists the branch sequence for each a and k, then I need to just calculate the in and out degree of each vertex of this graph. So we can see for this picture that on my picture, each of this graph has exactly 2 in and 2 out degrees, because, so for example, so here all the loops, of course, will count in as in degree and out degree. And so for each of these vertices, we have 2 in degree and 2 out degree. And so it is the same, and from the theorem we obtain that we have Euler circuit. And if we have Euler circuit, we have Euler Trail, and this means that we have the branch sequence. But for the arbitrary nk, let's look at this graph. So if we have, it's sometimes called the Debrev graph for arbitrary nk, and if we see, so our vertices is just the all sequences of length k minus 1, and if you look at the this vertex, that if we calculate the number of edges going in or out from this one, then we can see that, so what edges are going out? The edges are going out is all the sequences that has this first k minus 1 element. So the edges go out differ only by the last element. And so the last element will be, can be any element from the alphabet A. So we have A1, AK minus 1, and some element. Okay, I need to change the definitions of alphabet A. So we have here, you can, first of all, we start from A2 and ends in B1. We start from A2 and ends in B2. Start from A2 and end in Bn. And so the edges will be sequences of length n, which is starting from A1, AK minus 1, and ending in B1, B2, B3, etc., Bn. So we have exactly n edges coming out. And the same goes for the edges coming in. So for the edges coming in, I just wrote all the sequences or the words of length k, which begin from different elements of the alphabet A and ending in A1, AK minus 1. So it will be B1, AK minus 1, B2, A1, AK minus 1, and B, and A1, AK minus 1. And we start from the words B1. B1, A1, etc., AK minus 2, B2, A1, etc., AK minus 2, and so on, Bn, A1, AKN minus 2. So we have out and n degree will be equal to n for the all vertices of the graph, and so we will have the branch sequence. So for all vertices we'll have in degree equal to out degree equal to n, and this means that we always obtain there always exists a branch sequence. So we have a proposition exists for all A and K. And this answer for the first question is the sequence always exists. And of course, we can have different Euler trails. So we can just write another circuit and then cut it from the each edge, and we have different Euler circuits here. So we have plenty of different De Bruijn sequences. And the next interesting question is, can we provide some algorithm to drawing the De Bruijn sequence? And so I will just now make it an exercise. So I will just provide an algorithm, and your task will be to prove that this totally works. So example of the algorithm. Okay, so now I need to be sure that it will work, but I think we will. So for the 0, 1, we'll have for the 0, 1 and length k. I think if you, so I will write this for 0, 1, but of course it can be generalized for all alphabets. And I think if you look close, you understand how to generalize it. The first step 1, begin with all ones. So we just wrote the word that contains only ones, and then so if try to write 0 at the end, if it is okay, continue. If it's not, write 1. So what does it mean, okay or not okay? So if it is not okay, if the sequences that we add to the new words of length k is we already have this as a word earlier in our sequence. So if we cannot write 0 here because there will be repeating words of length k, then try to write 1. So this is called 0 better than 1. This strategy is called 0 better than 1, or prefer 0 to the 1. Okay, so for example, if I need to write the De Bruijn sequences for 0, 0, 1, and length 4, so what should I do? I should write the 4 ones, then I should write 0 because 1, 1, 1, 0 is never occurred in this sequence. Then I will again can write 1, can write 0, again 0, again 0. But then I cannot write 0 because if I wrote 0 here, then we will have the same word of 4 zeros. So I cannot write 0 here. So instead of it, I write 1 and have 0, 0, 0, 1. Again, so I just look, can I write this 0? I just need to check if I meet these sequences already, but I don't need the sequences. So I can write 0 here, and again I can draw 0 because this sequences was never occurred. But now if I wrote 0, it will be the same words as here. So I can write 0 here. write 1. 0, 1, 0, 0, 1 was never occurred in my sequence. Then 0 I cannot write because I already have 0, 0, 1, 0 here. So I wrote again 1. 0, 0, 1, then will be 0. Then 0 I cannot write, so I wrote 1. So I think that will be all sequences. So I'll have 4, 8, 12, 16, 17. Oh no. Maybe I need one more 0 here. Yes. Yes. So 0, 1. Oh, I should write 0 here. Yeah, and then 1, 1. Yeah. So I can maybe forget about all the zeros and yeah. This one, this one, this one, this one. Yeah, 1. Yeah. Okay, so it'll be 1, 2, 3, 6, 9, 12, 15, 16. Yeah, so this is the same. Yeah. So, for example, for 0, so for the 0, 1, and 4, its algorithm worked. And of course, if you need, if you have more letters, so not 0 and 1, but I don't know, letters like A1, A2, etc., AN. So we need to order them. Like in this sequence, we have need to use the rule A1 better than A2, then A3, and so on. And we start from the sequences with all AN, and then we try to add A1. If we cannot add A1, we just try to A2, A3, and so on until AN. And if you wrote all the sequence, then so the proposition that using this algorithm we will get the De Bruijn sequence. So the proposition we will obtain and this is much easier than just knowing that we have an Euler circuit, an Euler trail. So because this is the straightforward algorithm, so you can just write easily code on Python to write this De Bruijn sequence because so just you check that this word's not okay. So and there are different types of this algorithm, so we just need to prove that this algorithm works. Okay, so I just maybe I will give you a 5 minutes to think about this algorithm and maybe just try to use them for drawing the length 5 or just take the alphabet of ABC and try to do this algorithm for lengths 2 or 3, just to understand how it works, or just try to prove if it's working or why it's working. So we have this exercise and the proof of this proposition. Okay, so let's do an example here of length 2. Yes. So we start from, if we say that A is better than B is better than C, then we start from CC. Then we try to route A. Okay, then we try to route A again. It is okay. Then we try to route A, but we cannot route A because it will be the same sequence as before. So we route B here. Then again we try to route A. Then we cannot route B, so we write C. And in B, so we wrote C here. After C, we cannot route A because we already made the sequence, so we wrote B. After it, we cannot route A, so we wrote B. Then we cannot have A and B, so we wrote C here. And that's all, I suppose. And we have 1, 2, 3, 4, 5, 6, 7, 8, 9 sequences. We have already 9 sequences of length 2 in the alphabet of 3 elements. So it is correct.
And this one, like permutations, how can I say it? This one we can have more than one solution for this one. Like it doesn't matter.
Yeah, of course, we can have more than one de Bruijn sequences. But now I provide the concrete algorithm. So I just start with CC and then add the first element of the sequences that are not occurred before. So I just try to A or maybe B or BBC. Of course, I can provide different. So you ask about is your sequence is de Bruijn sequences? I can answer that. So what is your sequence?
Sorry, again, I didn't understand the question.
Sorry?
I didn't understand.
You understand the algorithm?
No,
why?
I understood, but you asked in the end, they asked a question, I didn't understand it. You asked, right?
Sorry, could you repeat please, because
I understand everything. Everything is okay. There is nothing wrong.
okay.
I understand.
So of course, I think you can provide this algorithm for the length 3. So for example, so we have 27 words of length 3 in alphabet of 3 elements. So this sequences will be length of 29. It's a bit long, but I will try to provide it. So we have CCC, then A, then we can repeat, then we wrote B, then again A, then we can again wrote A, then C, then A, A was already here, so we wrote B, A was already here, so we wrote B, B, A, B, B, and BB, so was already here, so we have ABC, BCA, CA, and B was here, so we wrote C, AC, A was already here, so we wrote B, CB was not here, so we wrote A, BA, C, AC was already here, so we wrote ACC, CCA was already here, and so we wrote B, CBA was already here, so we wrote B, CBA, so we obtained BBB, and then C, BC, BCA, so we have BCB, CBA, CBC, and PCA. So that's all. Okay, so what is the length of this sequence? 3, 6, 9, 12, 15, 18, 28. And I need 29. Oh, so I need to write BCC, yes. Yeah. Okay, so it will be exactly 29, which is the length of this different sequence. Okay, but the main question is why is it works? So the easiest part maybe is that, so we start from the, so I will write this for 0 and 1s, but the same idea will call for arbitrary situation. So if we start from all 1s, so it, oh, maybe it's not easy to see what sequence will be the ending of it, yes? Yeah, but since our graph, so the easiest part is that where we end in this. So suppose we cannot provide the next step of our algorithm. Could you please say what were the last elements of this sequence, which we wrote using the algorithm 0 is better than 1? Sorry. Yeah. So I state that the last sequence should be all 1, 0, all 1s. Do you understand why?
Yes.
Why?
Because it will be like in the example of K4. It will be the case where we have it's.
Sorry, what? Could you repeat?
It's like in the example where we had K equal 4. It's always we will have the K minus the first one will be 0 and we'll have K minus 1 and
yeah, again, but can you prove it? So why is it so? It is the same idea from the proving this theorem about Euler graphs, because if we start, so in our De Bruijn graph, we start from the node where I have all 1s, and then we go under some edges, through some edges of this graph, using this algorithm. So each algorithm is just another edge. And if I can go through this algorithm, this means that I finished only with in vertex when we have when we started, because otherwise we have in and out degree are the same. That means that we can always continue our path. So we end in the same vertex. So it's easy to understand that we finish in the same vertex that we started. So we started from the all 1s, then we finished again in sequences of all 1. It is the easy part. And the hardest part is to show that we actually meet all the edges in this path. So we exactly go through all of the edges before we came to the all 1s here. And so the main idea is that so if I just show the idea of the proving, the idea is that if we finish on the sequence of all ones, it means that we so what can happen? Suppose we not meet the sequence some subsequence. So we have like x1 etc xk, where xj is 0 or 1, and it doesn't contain here, doesn't belong here. We don't have it in the sequence. This means that we didn't pass through one of the edges in this De Bruijn graph. So we didn't use this edge when we're going by this rule through all the graph. But what does it mean? So if we, it means that we have some node, and we have some edge going out of this node, which we do not pass. So we have here x1, etc., xk. And this vertex must be x1, xk minus 1. So if we have exactly two options here. Either we do not pass through this vertex at all, so we do not get here going using this algorithm, or we was only once here, and this means that xk is equal to 1. So we have two options. If xk is equal to 1, then we meet one time this vertex, and if xk is 0, then we doesn't meet this vertex at all. But if we do not use so what does it mean that we meet it one time or 0 times? So 0 time, it means that we didn't so we have x1 xk minus 1, and we have this is going to x2 xk minus 1 0, and x2 xk minus 1 1, and we get here from the sequences 0 x1 xk and 1 x1 xk. So I just now I just parallel some ideas, so that if we do not meet some edge, then we do not cross the one of the more vertices 1 or 2 times, and then we can just try to go to the previous the previous vertex and try to see if they meet them once or twice, and try to find the so like the minimal the first edge, the first vertex that we did not meet twice using this algorithm, and then just try to find the contradiction. So I just want to maybe we'll sketch it and go straight forward to the proof. Okay, so how to take step forward to the proof. Okay, let's again look at the De Bruijn graph, but now let's look only of the edges that end on the 0 or end on the 1. So I just draw a picture, I think, for sequences of length 3, because it will be so big picture. So I have here I have 1, 1, 1, 1, 1, 0, 1, 0, 1, 0, 1, 1. Okay, maybe I will need to get my space. Okay, then I have the edges, but now I want to color them different colors when I add 1 at the end and when at the end 0 at the end. So for example, here I add 1, here I add 1, 0. Что за подсказки на русском? Sorry. So 1, 2, 3, 4, 5, 6, and I have exactly 2 more, which will be 1, 0, 1, I have 2 zeros, yes, so 2 zeros, 1, 1, which is 2, 0, 1, 1, yeah. 0, yeah, I don't know. 2, 0, 1, 1, and 1, 0, 1, 0, 1, 0, 1, 0, 1, it is this one. Okay, if you look here, so you can see that we have a tree here of the green edges. So if we add only 1, we have 3 here, and if we add 0, again we have the same tree but without the construction. So here we have 0, 0, 0, 0, 1, 0, 0, 0. So if it ends on 2 zeros, okay. If it ends on 0, 1, it will be this one, and ends on 0, 1, this one, 0, 1, 0. If it ends on 1, 1, then we have here 1, 1, 1, 0, and here 0, 1, 1, 0. Okay, and the last one will be 0, 1, 0, 0. And it ends on 1, 0. It will be yeah. And I forget just one edge, which will be calculated by the in and out degree. So from this guy, yeah, this one. 0, 0, 1, 0, 1, 1, 0, 0. Okay, how is this two trees, red and green, helping out to prove our statement that we meet? So we will have the different sequences using 0 better than 1. So in these terms, I can see that we're working through our graph using the rule that if we, so firstly we need to use red edge, then green edge. So we start from this vertex and go through the rule, use the rule that we're going through the right edge, and if we can go out using right edge, then we use right edge, and then if we cannot use right edge, we use green edge. Okay, can we prove that we go through all the edges of this graph? So if we use this algorithm, then we will go through all the edges of the graph. So how can I prove it? So if I'm already show you that if I started here and go through the right edge, then I finish here by using this green edge. So if I use this green edge, then before I use this green edge, and then I use this red edge. If I use here, that it means that I use. So if I prove that in each previous vertex I use all, of course if I use the green edges I use the red edge, but I need to be sure that I use all the green edges here. And so if I use all the green edges, of course I use already all the red edges, and so I use all the edges to leaving this in my circuit. So I need just to somehow prove that I use all the, for example, so I need to check all the green edges in my root. So I need to use just the notion that, okay, so the idea is that, so if I go here, this is the last element of the green tree. That means that I walk. So if I go from each vertex by the green edge, that means that I already visited twice, and that means that I walk in twice. So for example, for this vertex, I already go out of the green that I meet twice. That means that I use all these two green vertices here. If I go out from this vertex using green edge, that means that I visit previous elements of the green tree. Because if I go out using the green edge, it means that I already was there and go out from the red edge. So if I go out with the green edge, that means that I visited this vertex twice. So I visited this vertex twice, then I visited the previous vertex twice, and then all the previous vertices are visited twice. So if I go starting from this and go up from the green tree, I can prove that I visit all the vertices in this green tree twice, which means that I visited go through all the edges. Okay? It's hard, yeah? It's hard. But the idea is not, so I just look at the green tree, and look at the first node which wasn't visited twice. So so if I wrote the green tree and look at the first element of this green tree, which is not visited twice. So, for example, this one. But if I use, if I visited the all consecutive verses twice, it means that I go throughout this edge. Going throughout this edge, it means that I used the green edge from this vertex. And if I use the green edge from this vertex, this means that I already used red edge from this vertex. This means that I visited this vertex twice, which is a contradiction to what I told before. Okay, no. Okay, maybe I will write some text here. Suppose there exists a node V such that all the we visited the next green vertex after we visit double twice, and we have this situation. But visit V less than 2 times. But if we visit double twice and this arrow is green, that means that we go out. So we already visited V because we used this green arrow, and because we visited double twice. So we visited this green arrow. So we visited V. And if we use green arrow, then already we used red arrow. But we visited double twice, which means we used green edge from V, which means that we already used red edge from V. This means that we visited V twice. So if we visited some node twice, that means that all previous nodes that goes from this using green edge, we already visited twice. And so if we have green tree and we visited the terminal leaf of the tree twice, it means that we visited all the previous nodes twice, which means that we visited all the edges. Okay, I think I just repeated the same argument 2 times. So maybe we can think about it. Yeah. Understand? Maybe you have questions? Okay, maybe we'll think at home with this and then I will repeat. Yeah. Yeah. So I think at the beginning of the next lecture, I will just repeat the same argument and we can discuss it if you have questions.